Welcome. Today, we're going to dive into a really powerful set of techniques that, honestly, every competitive programmer and algorithm enthusiast should have in their back pocket. We're talking about square root algorithms. So you've been there, right? That classic coding dilemma. You've got a problem, and the straightforward O of N solution is just going to be too slow. It'll time out for sure. But then the super optimized O log N data structure, like a segment tree or something, feels like it's just out of reach, or maybe it's just way too complicated to code under pressure. It's a really frustrating spot to be in.
Well, guess what? There's this fantastic middle ground. Square root algorithms, which often run in something like O of n rad n or have queries that take O of rad n, are that perfect, good enough solution. They can be the difference between getting a time limit exceeded and seeing that beautiful green accepted. And they're often way simpler to code, which means less time debugging and a much lower chance of making a critical mistake when that clock is ticking down.
So in this explainer, we're going to go on a little journey. We'll start with the core idea of blocks, then see how we can combine algorithms, look at a pretty neat math trick, and then tackle the famous Momos algorithm. And we'll wrap it all up with a checklist to help you spot exactly when to use these techniques. Okay, let's dive right in. First up, the core idea of blocks. This is really the fundamental concept. It's called block decomposition, and you're going to see this idea pop up again and again in different forms. So for your exams, the key definition here is that we're splitting a big array into a more manageable number of chunks. Think of it like a huge library. Instead of searching every single book on every shelf, what do? You first find the right section. That's our block. And then you only search the shelves inside that one section. It's a simple but really powerful way to organize things. Let's make this a bit more concrete with a classic problem. Imagine we have an array, and we need to do two things really efficiently. One, update the value of a single element, and two, calculate the sum of all the elements inside a given range. The way we query this is a three-part strategy. For the big middle part of our range, we can just instantly grab the pre-calculated sums of the full blocks, super fast. But for the edges of the range, the parts that only partially cover a block, we have to go in and sum those elements one by one. By combining these two approaches, we get this nice balance between speed and simplicity.
And this slide just brilliantly shows the central trade-off. This is a key point to bring up when you're structuring your answers. Updating an element is now crazy fast, O of 1 time, because all we have to do is change the value in the array and then update the sum for that one block it belongs to. The cost? Well, our range sum query is a bit slower now, taking O of root n time.
So the whole point, the crucial idea, is this concept of balance. Why square root of n? Because it makes sure that both of the slow parts of our query are about the same size. We have to iterate over, at most, square root of n full blocks. And those messy little edge parts at the beginning and end, they also involve, at most, about square root of n elements each. It's this balance that gives us that sweet O of the square root of n complexity.
Okay, next up, let's see how we can build on this. The square root idea isn't just for chopping up data. It's also a really powerful way to combine two totally different algorithms, using square root of n as the point where we decide which one to use. Let's think about a new problem. We're given a grid full of letters, and our job is to find the pair of identical letters that are closest to each other. Now, we could try to solve this in two kind of naive ways. Algorithm 1 is simple. For any letter that shows up k times, we just check every single pair. This works great if k is small, but it's awful if a letter is super common. Algorithm 2 uses a breadth-first search, or BFS. This is fast if a letter is common, but if we have tons of unique letters, we have to run a whole bunch of separate searches, which gets really slow. A common mistake here is just picking one and hoping for the best. The elegant solution is to just combine them, using square root of n as our cutoff. If a letter is rare, let's say it appears less than or equal to square root of n times, we use the simple pairwise check. If it's common, appearing more than square root of n times, we switch to the BFS. This hybrid strategy makes sure that neither of the worst-case scenarios can ever bite us, and it gives us a total runtime of O(n) root n. This is the perfect structure for an exam answer, by the way. Identify two naive solutions, point out their weaknesses, and then present the hybrid approach that balances them. Okay, now for something a little different. A surprising math trick, where this whole square root idea just kind of pops up in an unexpected place, but with direct consequences for our algorithms. So here's the rule. If you want to break down a number n into a sum of unique, positive integers, you actually can't use very many of them. At most, you'll have something on the order of the square root of n terms. Think about it. To get the most parts, you have to use the smallest distinct numbers you can, right? Like 1 plus 2 plus 3 and so on. But that sum grows quadratically, so you run out of room inside of n really, really fast. And this isn't just some math curiosity. It has real-world applications. In a knapsack problem, this rule tells us we can group items by their weight because we know there are only about O root n distinct weights possible. This trick lets us improve a standard dynamic programming solution. The exact same logic can apply to strings, where we can group them by length. So this isn't just theory, it's a concrete way to optimize your code. All right, our final major topic is Mohs algorithm. And this is a truly clever technique that applies that block idea we talked about, but not to the data itself, but to the questions we're asking about the data. Okay, first, a really crucial definition. Mohs algorithm only works on what we call offline problems. This just means we get all of the queries up front, and the array we're working with never changes. This is huge because it gives us the freedom to answer the queries in any order we want, not necessarily the order they came in. This is a common place to make a mistake. You absolutely cannot use Mohs if the array gets modified between queries. The central idea is just beautiful. We maintain a single active range with 2 pointers, a left one and a right one. And to answer a query, we just slide these pointers around to match the query's range. The real magic is in sorting the queries in a special way so that the total distance our pointers have to travel is as small as possible. And here it is, the specific sorting rule you need to code up. First, you group all the queries based on which block their left endpoint falls into. Then, inside each of those groups, you sort the queries by their right endpoint. This special ordering makes sure that the left pointer only makes a few big jumps, while the right pointer just kind of sweeps back and forth smoothly. It's really clever. So, what's the results of all this clever reordering? Well, for problems where you can add or remove an element from your range really quickly in O of 1 time, the total complexity for n queries on an array of size n becomes a remarkable O of n root n. Okay, so to wrap all this up, let's distill everything down into a simple revision checklist. You can think of these as the mental triggers to look for when you're tackling a new problem. So when you're stuck, just ask yourself these 4 questions. Is there some kind of balance to be struck between 2 operations? Can I combine a fast for small inputs algorithm with a fast for large inputs one? Am I secretly dealing with a limited number of distinct items? And finally, if I've got range queries on a static array, can I go offline and use Mohs? This is your problem-solving guide right here. We've seen that the square root isn't just a number, it's a powerful idea. It's about balance, about trade-offs, and about finding these clever middle grounds. So the next time you see a problem that seems too slow for one approach and maybe too complex for another, remember this sweet spot. Thanks for watching.